Welcome back, everybody. Today we are going to be continuing our discussion of chemical reactions, taking a look at how certain ionic compounds are going to dissociate into solution into their respective positive and negative ions, right? Their cations and their anions. And we're going to see that when we have combinations of different soluble ionic compounds, that it's not every ion that's going to actually participate in the reaction. Some are going to be soluble in the beginning and some are going to be soluble in the end. And so in reality, those ions are not participating in any chemistry. We're going to see how we can take an overall reaction that shows the complete ionic compounds that are combining to form some new compound in a double displacement reaction. And we're going to see how we can break down that reaction to give what's called the net ionic reaction, which is going to much more succinctly show exactly what is participating in the chemistry that we are describing. We're going to take a look at a few other reaction types and see how we can understand the reactions for those as well. But we really are going to focus quite a bit on this net ionic reaction, as it is a fundamental first reaction to understand as you're going through chemistry. So without much more, let's get into the video. So today we're going to be discussing solubility, and the key point of this is substances have a property called solubility, for which the amount that we can dissolve is called its solubility. And what we'll see is that some compounds are very soluble and others are not soluble or insoluble. So for example, sodium chloride is very soluble, right? If we are to take 365 grams of sodium chloride and put it into 1 liter, that many will dissolve, right? That much is soluble. So that is the maximum per liter, right? If we were to put in less, it would be just fine. But if we were to put in more, that's sort of the maximum. But 365 grams, that's almost a pound of salt, and 1 liter of water, right? Like an individual drinking water bottle is half a liter. So putting a pound of salt into 2 of those, quite a bit of salt. Conversely, something like silver chloride in water has a very low solubility, so that same amount of water, 1 liter, can only accept 0.009 grams, or 9 milligrams. And so we would call this one insoluble. And for all intents and purposes of this course, we're just going to divide salts into those 2 categories. When I say salts, I mean an ionic compound. We're really going to focus on ionic compounds mostly here. Either they're soluble or they're insoluble. This really is sort of the magnitude that we see on insoluble versus soluble. There's not a ton of in between, right? Most things either are soluble in an appreciable amount or they're basically not soluble at all. So we will use a list of rules. I have some guidelines that can help us along the way as well. And for those rules, please see chapter 4.2. That's where the solubility chart is in OpenStax. Definitely make sure you consult that table for details on solubility, but as far as just a good estimation in your head, as well as some known chemicals that are always going to be soluble, we can use the rule NCAA number 1. So N is nitrate, C is chlorate, A is acetate, the second A is ammonium, and the number 1 means group 1 metals, right? Compounds containing group 1 metals. So basically, if we have any ionic compound containing one of these things on NCAA number 1, then we're going to be soluble, right? So if we have a group 1 metal, sodium or potassium, we want to think always soluble. If we have nitrate, NO3-, then we should also think always soluble, right? This doesn't cover every single soluble compound, but it does cover these cases, right? These ones will always be soluble, and I think that you'll find that if you can keep these cases in mind, the solubility of things will sort of jump out at you, right? If you see nitrate soluble, if you see group 1 metal soluble, and I would say those 2 are really the most common and the ones you should focus on to start. Okay, so keeping these rules in mind, which of the following is most likely to be insoluble? Go ahead and pause the video and register your answer, and we will discuss. All right, hopefully you paused the video and registered an answer. Take a look at the following, and the answer should be our lead iodide, right? Because as we see, the rest of them all have an anion or a cation that fits into this NCAA number 1 category, right? Sodium chloride has sodium, that's a group 1 metal. Calcium acetate has acetate, which is A acetate. Magnesium chlorate has the chlorate, which is the C here. The other 3 are all satisfied by NCAA number 1, meaning they're all soluble, and it's lead iodide that may not be soluble, most likely to be insoluble. Okay, so precipitation reactions occur when we have two soluble ionic compounds that react to form an insoluble compound. And basically this means we're going to form a solid precipitate in solution. And this is one of the classes of reactions that we're studying. Precipitation reactions will use these solubility rules. And generally we're going to have two different solutions with compounds in them that satisfy the solubility rules. So two soluble compounds, two solutions that are completely aqueous. And then when we combine them, the anions and cations will mix around in order to form an insoluble precipitate, we call that. So for example, what about the following? If we have silver nitrate plus sodium chromate, the question is, well, first, what are the products that are going to be formed, right? We want to be able to predict the products that are going to be formed here. And the way we do that, right, is by switching the anions and the cations. So the possible product would be the sodium chromate would switch with the silver and potentially give us sodium nitrate, and the silver would jump over to the chromate and potentially give us silver chromate. I mentioned potentially because, as we'll see, if none of these are insoluble, then we'll actually just sort of have the same situation as before, right? Just with all four ions in solution. Okay, first off, we're going to predict the products. I would encourage you to pause the video and predict the products. And keep in mind that when you predict the products, they must be balanced with respect to the charge from the cation and the anion. So go ahead and pause, try to write those down. All right, so hopefully you're able to predict some products. Here they are, right? We have the switch, so silver is going to go with the chromate, and sodium is going to go with the nitrate, and we propose that the following reaction is occurring. Now we do want to make sure that it's balanced. So is it balanced, right? Do we have a balanced reaction here? Go ahead and pause again, and if it's not balanced, I would recommend you balance it. Alright, so as we're looking at this, is the reaction balanced? I would say no, and right away if we look at the silvers, we can see that that's not balanced. So let's go ahead and go through our balancing process, and what I would highly recommend is to consider the polyatomic ions as a whole. We don't need to divide up into chromium and oxygen individually, because in this precipitation reaction, we're just switching our anion and our cation, right? So I wouldn't try to count the total number of oxygens. I think that would just make the math a bit more complicated. Balance the nitrates, balance the chromates, balance the silvers, and balance the sodiums. And let's take a look at how that works. We end up with the following, right? So I would say first we balance the silvers, and we say, well, we need 2 silver nitrates on the reactant side, so I would put that 2 in there first. And then scanning through again, I would see, well, looks like we have 2 sodiums and 2 nitrates on the reactant side, so we'll need to put a 2 in front of the sodium nitrate on the product side. And at that point, everything looks balanced. I hope that you can kind of see what I mean by not balancing every individual atom here, right? Because if we're trying to count up the oxygens, we're saying, well, I've got 4 in the chromate, and we've got 3 times 2 plus 4, so 10, and then you're sort of considering all 10 on the other side. And I think that's much more complicated than just focusing on the polyatomics as a whole. Remember, they're not going to break up in these precipitation reactions. All that we're doing is switching the cation and the anion. We're not breaking any of those covalent bonds that are part of the polyatomic ions. Okay, so now we need to decide which of these are insoluble, if any, right? We want to assign states to each of the compounds here. And so here we have our general rule, right? NCAA number 1, nitrate, chlorate, ammonium acetate, or group 1 metals. And go ahead and use those guidelines to assign states to each of these ionic compounds. Go ahead and pause, try that one out, and we'll discuss. All right, hopefully you're able to assign some states. And what we see here is that 3 of these, right? The silver nitrate contains nitrate, so it's soluble. Sodium chromate has sodium, so there we go. Sodium nitrate, sodium as well. So those are all going to be soluble by this guideline, NCAA number 1. But what about silver chromate? So we see that it doesn't fit the rule, which again doesn't necessarily mean that it's insoluble, but it does mean that it's not definitely soluble, right? Solubility isn't quite as cut and dry as NCAA number 1, and while it does cover compounds that are always soluble, it doesn't cover all the compounds. So what we want to do is we want to pull up a table from chapter 4.2, our solubility table, and we can see the following over here, right? So we see insoluble ionic compounds that contain the following ions, and you should really pull up your table and make sure you're seeing this part as well. But it's saying that if we contain the chromate ion, so CrO42-, that's the anion we're looking at here, then it's going to be insoluble with the exception of compounds with group 1 cations, that's part of our NCAA number 1 rule, or ammonium, which this one isn't. And so therefore we can conclude that this is insoluble, and we're going to give it the solid state notation. It's an insoluble ionic compound, meaning it's going to be solid in solution, and so we want to denote it that way. And as we'll see, this is very important for the actual chemistry that's going on with this reaction. So this is our proposed reaction. We have a balanced chemical reaction. We have reactants and products. We have the states. But what we're really interested in is what exactly is going on. What is our net ionic reaction? In other words, meaning just the chemistry that's occurring. And so we're going to break down the process on how to get that net ionic reaction, and I think you'll see how it's a useful component for this. So to convert from our balanced chemical reaction, which is what this is, to our total ionic reaction, what we want to do is we want to write all aqueous compounds as individual anions and cations. And so that would give us the following. Definitely be mindful of your coefficients and your subscripts, right? I've been pretty intentional with how I've provided this here. If we have 2 silver nitrates, that's going to dissociate into 2 silvers plus and 2 nitrates. And so we're going to have 2 silver pluses and 2 nitrates as that first bit. Still aqueous. This is really the definition of these aqueous ionic compounds that dissociate completely, right? When we say AgNO3 aqueous, what we really mean is that it's existing not as an AgNO3 package, but as a silver ion and as a nitrate ion. And so that's our first part. We do the same thing for the sodium chromate, noting that there are 2 sodiums. So we end up with 2 Na pluses, and we end up with that CrO42-, our chromate. We don't break up the silver chromate, though, because it's solid. It's not going to be soluble, and it's not going to break up. So that one we leave as is. And finally, we do the same thing with the sodium nitrate, which is really the same process as the silver nitrate. And so this is the chemistry that's occurring, right? When we mix the 2 solutions together, the soluble silver nitrate plus the soluble sodium chromate, we have all 4 ions floating in solution just at that instant when we mix things together. But as soon as the silver and the chromium chromate meet, they form silver chromate. But the sodium and the nitrate are still dissociated, right? If they would dissociate in solution, there's no reason putting them in together would make them associate, right? And so we notice here that those ions are actually in the exact same state on both sides. And we call those the spectator ions, and we should highlight them, right? In the process of going to our net ionic reaction, you maybe want to circle them, underline them, but somehow note that these are your spectator ions, and note that they're actually not engaging in any chemistry at all. They're exactly the same on the reactant as the product side. So we're almost done, right? The only final step is that we want to show the reaction without those spectator ions, basically rewriting it to ignore the spectator ions. And so we end up with the following net ionic reaction, where the chemistry that's occurring is that 2 silver plus ions are joining with the chromate 2- anion and is forming solid silver chromate. And so, again, the point of the net ionic reaction is to show just the chemistry that's occurring. Spectator ions are still very important. They bring these ions into solution, right? We can't just have silver plus sitting on the shelf without a counter ion. But they're still unchanged, aqueous before, aqueous after, dissociated before, dissociated after, and therefore the only chemical change that's occurring is that this silver chromate is being created. Alright, so that is all I've got for precipitation reactions and net ionic reactions for this video. Definitely a very important process, so hopefully you understand each of these steps. If not, I definitely recommend you study them. And I would say the most challenging chemistry part here will be the predicting of the products. So make sure you're predicting your products properly. Remember your ionic charge balancing, that we need to have the same contribution from positive and negative. And I think that once you go through, breaking to the total ionic, into the net ionic, with a balanced chemical reaction with proper product predicted, I don't think you'll find that too unapproachable.